Right now, as you sit or lie in comfort, something extraordinary exists just beneath your feet. A world so vast and mysterious that most of us never pause to consider its presence. This is not a world of sunlight and open skies, but one of eternal darkness, ancient silence, and secrets that have been locked away for millions of years. Imagine, if you will, taking a journey downward, not just a few feet into rich garden soil, but deeper, much deeper, past the roots of the tallest trees, beyond the reach of any shovel or drill you might find in a garage. We are going to descend into a realm that stretches for thousands of miles beneath us, a place where the familiar rules of our surface world no longer apply. The ground beneath your feet is not simply dirt and rock. It is the thin ceiling of an immense, hidden universe. This world pulses with life in ways that would astonish you. Strange creatures move through caverns larger than cathedrals. Ancient waters flow through channels carved by time itself. And far below, in the crushing darkness, forces work quietly to shape our planet in ways we are only beginning to understand. Tonight, we invite you to forget about the world above for a while. Let your mind sink down through layers of earth and stone, following us into the depths. We will move slowly, gently, like settling into a warm bath of discovery. There is no hurry in this underground realm. Time moves differently here, measured not in hours or days, but in the patient erosion of stone and the slow dance of geological forces. As we begin this journey together, take a deep breath and let yourself relax. The hidden world beneath our feet has been waiting for millions of years. It can wait a little longer as we explore its wonders with the reverence they deserve. Close your eyes if you wish, and let your imagination carry you downward into the secret heart of our living planet. This is a world where silence speaks volumes, where darkness reveals hidden truths, and where the impossible becomes everyday reality. The deeper we go, the more we discover that our planet is not a solid ball of rock, but a layered mystery. Each mile downward reveals new wonders. Ancient minerals that have never seen daylight glitter in hidden chambers. Vast networks of stone tunnels wind through the darkness like the arteries of some enormous sleeping giant. The temperature rises as we descend, not from any fire or flame, but from the very heart of our world itself. The pressure increases with each passing mile, creating conditions so extreme that they would crush anything from our surface world in an instant. Yet life persists here, adapted to these harsh conditions in ways that challenge everything we thought we knew about the limits of existence. Deep beneath the familiar world of grass and trees, of cities and oceans, lies a realm that operates by different rules entirely. Here, time is measured not in human lifespans, but in geological ages. Here, the very rocks flow like thick honey, reshaping themselves over millions of years. Here, in the deep darkness, our planet reveals its true nature as a dynamic, living system of incredible complexity and beauty. Welcome to the mysterious realm that lies beneath us all. A world as alien as any distant planet, yet as close as the ground on which you rest. Beneath the ground we walk, a secret realm stretches far beyond what we can see. Dark, quiet, and mysterious. It is a world of ancient rocks, hidden waters, and life that thrives in eternal night. Tonight, we journey beneath our feet to discover the hidden world. Though unseen, the Earth's structure is a story written in stone and heat. As we begin our descent into the hidden world beneath our feet, we must first understand the magnificent architecture of our planet. Like an enormous onion with layers upon layers, Earth reveals its secrets only to those patient enough to look deeper. The journey begins just beneath the surface, in what scientists call the crust. This is the thin skin of our planet, the only layer most of us will ever touch or see. Yet even this familiar ground holds mysteries that have taken scientists centuries to unravel. The crust varies in thickness like the peel of an orange, thin in some places, thick in others. Beneath the oceans, it stretches down only about 4 miles. But under the great mountain ranges, It can extend 25 miles deep or more. Picture yourself standing at the base of Mount Everest, craning your neck to see its towering peak nearly 6 miles high. Now imagine that same distance, but going downward through solid rock instead of upward through thin mountain air. That is just the beginning of our journey through the crust. Here, in this outermost layer, temperatures rise slowly but steadily with depth. For every mile we descend, the temperature around us would grow warmer by about 60 degrees Fahrenheit. What starts as a comfortable room temperature at the surface becomes uncomfortably hot just a few miles down. The crust itself is not uniform. It comes in two main varieties, each with its own character and story. Oceanic crust, which forms the floor of our seas, is relatively young and thin. Most of it is less than 200 million years old, constantly being created at underwater mountain ranges called mid-ocean ridges and destroyed at deep ocean trenches. It is made primarily of dark, heavy rock called basalt, formed from cooled lava that once bubbled up from the depths. Continental crust tells a different story entirely. It is older, thicker, and more complex. Some parts of the continental crust are nearly 4 billion years old, making them among the oldest rocks on Earth. This ancient stone has been recycled countless times, melted and reformed, folded and twisted by the immense forces operating deep within our planet. Continental crust is made of lighter rocks like granite, which is why continents float higher on the mantle beneath them, like icebergs floating on water. As we move through the deeper parts of the crust, we encounter rocks that tell stories of incredible transformation. Here lie the metamorphic rocks, stones that were once something else entirely, but have been changed by heat and pressure into new forms. Limestone becomes marble, sandstone transforms into quartzite, and shale morphs into slate. These rocks are living proof of the dynamic forces at work beneath our feet, evidence that what seems solid and permanent to us is actually in constant, slow-motion change. The deeper we go into the crust, the more we encounter evidence of Earth's violent past. Here are rocks that have been shattered by ancient earthquakes, then healed by mineral-filled veins. Here are layers that were once horizontal seafloors, now tilted at impossible angles by the collision of continents. Every foot of depth reveals new chapters in our planet's 4.5 billion year story. At the very bottom of the crust, temperatures reach nearly 2,000 degrees Fahrenheit. The pressure has increased to thousands of times what we experience at sea level. Here, at the boundary between crust and mantle, we encounter one of the most important interfaces on our planet. This boundary, called the Mohorovičić discontinuity, or simply the MOHO, marks the transition from the familiar world of surface rocks to something entirely alien. The discovery of the MOHO was one of the great detective stories of geology. In 1909, a Croatian scientist named Andrija Mohorovičić was studying earthquake waves when he noticed something unusual. The waves seemed to speed up dramatically at a certain depth beneath the surface. This could only mean that they had entered a different type of material, something denser and more uniform than the complex rocks of the crust. Without ever leaving his laboratory, Mohorovičić had discovered the boundary between Earth's outermost layer and the vast realm that lies beneath. Beneath the crust lies a realm so vast and alien that it challenges our understanding of what solid matter can become. This is the mantle, a layer that makes up more than 80% of Earth's entire volume. If our planet were an apple, the crust would be thinner than the apple's skin, and the mantle would be nearly all the flesh beneath. The mantle extends down nearly 1,800 miles from the bottom of the crust. To put this in perspective, if you could somehow drill straight down from New York City, you would have to go deeper than the distance from New York to Denver before reaching the bottom of the mantle. This is a world of rocks so hot that it behaves more like thick honey than the solid stone we know on the surface. The mantle is divided into distinct regions, each with its own characteristics and behavior. The upper mantle, closest to the crust, contains a zone of particular interest called the asthenosphere. This layer, whose name means weak sphere, is where the rock is hot enough to flow more easily. It is like a cushion of partially molten rock that allows the rigid plates of the crust to move slowly across Earth's surface. Below the asthenosphere lies the lower mantle, a vast region that extends down to the core boundary. Here, the pressure becomes so intense that it actually changes the crystal structure of the rock itself. Minerals that exist in one form in the upper mantle transform into denser versions of themselves, like actors changing costumes for different scenes in the same play. These phase transitions create distinct layers within the mantle, each with slightly different properties. Throughout the mantle, temperatures range from about 2,000 degrees Fahrenheit at the top to over 7,000 degrees near the bottom. These are temperatures that would instantly vaporize any material from our surface world. Yet the immense pressure at these depths keeps the rock from melting completely. Instead, it exists in a strange state between solid and liquid, flowing so slowly that its movement can only be measured over millions of years. The mantle is not a still, quiet place. Deep currents of hot rock rise from the depths like enormous, invisible geysers, carrying heat from the planet's interior toward the surface. These convection currents are the engines that drive the movement of continents above. They push and pull at the crust, creating the earthquakes and volcanic eruptions that remind us of the dynamic forces at work beneath our feet. Picture a pot of thick soup slowly simmering on a stove. Hot liquid rises from the bottom, cools at the surface, then sinks back down to be reheated. The mantle works in much the same way, but instead of soup, we have rock heated to thousands of degrees, and instead of minutes, the cycle takes hundreds of millions of years to complete. This grand circulation system has been operating for billions of years, slowly but constantly reshaping the surface of our planet. Some of these mantle currents create hotspots, regions where particularly hot rock rises toward the surface. These hotspots can remain in roughly the same location for millions of years, creating chains of volcanoes as the crustal plates move over them. The Hawaiian Islands are a perfect example of this process. A string of volcanic peaks created as the Pacific Plate moved slowly over a stationary hotspot in the mantle below. Scientists have learned about this hidden realm not by traveling there, which is impossible, but by listening to its whispers. When earthquakes occur anywhere on Earth, they send vibrations called seismic waves racing through the planet's interior. These waves travel at different speeds through different materials, and by carefully timing their arrival at monitoring stations around the world, researchers can map the hidden structure of Earth's interior. It is like trying to understand the inside of a locked treasure chest by tapping on its sides and listening to the echoes. The waves tell us that the mantle is not uniform, but contains regions of different temperature and composition. Some areas are slightly hotter or cooler, creating the convection currents that drive geological activity on the surface. These temperature variations show up as faster or slower zones for seismic waves, allowing scientists to create three-dimensional maps of the mantle's internal structure. Recent discoveries have revealed that the mantle contains features as dramatic as any mountain range on the surface. There are vast upwellings of hot rock called superplumes that rise from the deepest parts of the mantle. There are also regions where cold, dense rock sinks downward, creating what scientists call slabs. These slabs are often pieces of oceanic crust that have been dragged down into the mantle at subduction zones, carrying water and other materials from the surface into the deep interior. The mantle also contains a surprising amount of water, not as liquid oceans, but as water molecules trapped within the crystal structure of minerals. Some estimates suggest that the mantle may contain several times more water than all the oceans on Earth's surface. This hidden water plays a crucial role in making the rock flow more easily and in generating the magma that feeds volcanoes. As we continue our imaginary descent through the mantle, the already extreme conditions become even more intense. The pressure increases to millions of times greater than what we experience at sea level. The temperature climbs toward that of the surface of the sun itself. We are approaching the boundary of another realm entirely, a place where the very nature of matter changes once again. At a depth of nearly 1,800 miles below the surface, we encounter one of the most dramatic boundaries in our planet. Here, the slowly flowing rock of the mantle gives way to something completely different. The change is so abrupt that seismic waves either bounce off this boundary or are dramatically slowed as they pass through. We have reached the outer core, a layer of liquid metal that surrounds the very heart of our world. The outer core is a sea of molten iron and nickel, heated to temperatures exceeding 9,000 degrees Fahrenheit. This liquid metal ocean is over 1,400 miles thick, a spherical shell of flowing metal that exists under pressures so intense they are almost beyond imagination. The iron and nickel here are not pure metals as we know them on the surface, but are mixed with lighter elements like sulfur, oxygen, and silicon, creating an alien alloy that exists nowhere else in our solar system. Here, currents of liquid metal flow and swirl in complex patterns that generate Earth's magnetic field, the invisible shield that protects us from harmful radiation from space. The movement of this liquid metal creates electrical currents, and these currents generate magnetism. It is like a giant dynamo spinning deep within our planet, creating the magnetic field that makes compass needles point north and helps migrating animals find their way across vast distances. The magnetic field generated by the outer core extends far into space, creating a protective bubble called the magnetosphere around our planet. This invisible shield deflects most of the charged particles streaming from the sun, preventing them from stripping away our atmosphere and making life on Earth possible. Without this hidden ocean of flowing metal, our planet would be a barren, lifeless world like Mars. The flow patterns in the outer core are incredibly complex, driven by the rotation of the Earth, temperature differences, and the chemical composition of the metal. Sometimes these flows can change or even reverse, causing Earth's magnetic field to weaken or flip its polarity. The North Magnetic Pole can become the South Magnetic Pole, and vice versa. These magnetic reversals have happened hundreds of times throughout Earth's history, leaving a record in the magnetism of ancient rocks. Finally, at the very center of our world lies the inner core. Here, at a depth of over 3,000 miles below the surface, the pressure becomes so immense that even at temperatures exceeding 10,000 degrees Fahrenheit, iron and nickel are compressed into a solid ball. This inner core is about the size of the moon, a sphere of metal so dense and hot that it challenges our understanding of matter itself. The inner core is not perfectly round, but appears to be slightly lopsided, with one side growing faster than the other. It spins slightly faster than the rest of the planet, completing an extra rotation about every 400 years. This differential rotation creates subtle variations in Earth's magnetic field that scientists can detect and measure from the surface. The boundary between the liquid outer core and solid inner core is another dramatic transition zone. Here, iron crystallizes out of the liquid metal, releasing heat and light elements that help drive the convection currents in the outer core above. This process has been going on for billions of years, slowly growing the inner core and maintaining the dynamo that generates our magnetic field. The inner core itself may have its own internal structure, with different crystal orientations in its eastern and western hemispheres. Some scientists think there may even be an innermost inner core, a region at the very center where the crystal structure of iron takes on yet another form under the extreme conditions found at Earth's heart. This incredible structure, from the familiar rocks of the surface to the alien realm of the inner core, has been revealed to us through centuries of patient observation and ingenious scientific detective work. We cannot journey there in person, but we can send our instruments and our imagination into these hidden depths, piecing together clues like detectives solving the greatest mystery of all, the nature of our own planet. Understanding Earth's layered structure helps us appreciate the incredible complexity of our world. We live on the surface of a dynamic, ever-changing planet where the continents drift slowly across the face of the globe, where mountains rise and fall over millions of years, where the very ground beneath our feet is connected to forces operating thousands of miles below. Each layer plays its part in the grand symphony of geological processes that make Earth the unique and vibrant world we know. Water flows even in the darkest depths, sustaining hidden life. As we continue our journey into the underground realm, we discover that water, the essence of life as we know it, does not exist only in the familiar rivers, lakes, and oceans above ground. Beneath our feet lies a vast hidden hydrosphere, a network of underground waters that dwarfs even the mightiest surface rivers. Imagine for a moment that you could drain all the visible water from Earth's surface. Every ocean, every lake, every river would disappear, revealing the true shape of our continents and sea floors. Yet even then, enormous quantities of water would remain hidden beneath the ground, flowing through cracks in rocks, pooling in underground caverns, and moving slowly through layers of sand and gravel in an intricate dance that has been going on for millions of years. The story of underground water begins at the surface, with something as simple as a raindrop falling from the sky. When rain touches the earth, some of it flows across the surface towards streams and rivers, but a significant portion seeps downward into the soil. This water begins a journey that may last decades, centuries, or even thousands of years before it sees daylight again. As water percolates down through soil and rock, it enters what scientists call the zone of aeration, where the spaces between soil particles contain both air and water. The water continues its downward journey, pulled by gravity, until it reaches a level where all the available spaces in the rock and soil are completely filled with water. This is the beginning of the zone of saturation, and the upper boundary of this zone is called the water table. The water table is not a fixed, unchanging surface like the top of a swimming pool. It rises and falls with the seasons, responding to rainfall patterns and drought conditions. In some places, it lies just a few feet below the surface. In others, particularly in arid regions, it may be hundreds of feet down. The water table generally follows the contours of the land above it, rising beneath hills and valleys, dipping beneath rivers and lakes. Below the water table lies the groundwater, a vast reservoir of fresh water that exists in the tiny spaces between grains of sand, in the cracks and fissures of solid rock, and in the larger openings of underground caverns. This groundwater represents the largest source of liquid fresh water on Earth, containing more than 30 times as much water as all the rivers and lakes on the surface combined. Groundwater does not simply sit motionless in underground reservoirs. It flows, though so slowly, that its movement is often measured in feet per year, rather than feet per second like surface streams. This underground flow follows the same basic principles as surface water, moving from areas of higher elevation and pressure toward areas of lower elevation and pressure. But the journey is far more complex, winding through a three-dimensional maze of rock layers, each with different abilities to store and transmit water. Some rock formations, called aquifers, are particularly good at holding and transmitting groundwater. These are often made of porous materials like sandstone, limestone, or layers of sand and gravel. Picture a giant underground sponge, soaked with water, and allowing that water to flow slowly through its structure. That is essentially what an aquifer is, though these underground sponges can extend for hundreds of miles and contain enough water to supply entire cities for decades. The most productive aquifers are often found in areas where ancient rivers and streams once flowed, leaving behind deposits of sand and gravel that now serve as underground highways for water movement. Some of these buried river channels, called paleochannels, were formed millions of years ago but still carry water today, connecting distant recharge areas where water enters the ground to discharge areas where it emerges as springs or feeds into surface streams. One of the most remarkable examples of groundwater storage is the Ogallala Aquifer, which lies beneath 8 states in the central United States. This vast underground reservoir covers an area roughly the size of California and contains enough water to cover the entire United States to a depth of 1.5 feet. The water in this aquifer fell as rain and snow thousands of years ago, slowly infiltrating through the soil and rock to create what is essentially an underground sea of fresh water. But aquifers are not the only places where underground water collects and flows. In regions with limestone, gypsum, or other soluble rocks, water can carve out extensive cave systems, creating underground rivers and lakes that rival anything on the surface. These karst landscapes, named after a region in Slovenia where such features were first studied, can contain vast underground water systems with their own unique ecosystems. The process of cave formation begins when slightly acidic rainwater, made acidic by carbon dioxide absorbed from the atmosphere and soil, comes into contact with limestone. The weak acid slowly dissolves the rock, creating small cracks and fissures. Over thousands of years, these small openings grow larger as more water flows through them, eventually creating caverns and underground rivers of remarkable size and beauty. Some of these underground river systems are truly enormous. The Sac-Acton cave system in Mexico extends for more than 215 miles, making it one of the longest underwater cave systems in the world. In these flooded caverns, crystal clear water flows through passages large enough for submarines, creating an otherworldly landscape of stalactites and stalagmites, visible only to the most adventurous cave divers. Underground water systems also exist in regions where you might least expect them. Beneath the Sahara Desert, one of the driest places on Earth, lies the Nubian Sandstone Aquifer, a vast reservoir of fossil water that was deposited during ancient times when the region was much wetter than it is today. This underground ocean contains an estimated 150,000 cubic kilometers of water, enough to supply the entire world's current water usage for over 1,000 years. The water in aquifers like the Nubian sandstone is called fossil water because it was deposited thousands or even millions of years ago, during periods when the climate was very different from today. This water is essentially non-renewable on human timescales, since the current climate does not provide enough rainfall to replenish what is being used. It is like mining liquid treasure from the depths of the earth, a resource that took millennia to accumulate but can be depleted in decades. The movement of groundwater creates some of the most beautiful and mysterious features on Earth's surface. When underground water encounters an impermeable layer of rock or clay, it may be forced to flow horizontally until it finds an opening where it can reach the surface. These natural discharge points create springs, places where underground rivers emerge into daylight, often forming oases in otherwise dry landscapes. Some springs are gentle seeps where water slowly emerges from the ground, creating boggy areas or small pools. Others are dramatic fountains where pressurized underground water shoots high into the air. The Blue Spring in New Zealand discharges over 400 million gallons of crystal clear water every day, maintaining a constant temperature year-round because the water comes from deep underground where surface weather has no effect. Geothermal springs add another dimension to the underground water story. When groundwater flows deep enough to encounter the heat radiating from Earth's interior, it emerges at the surface as hot springs or geysers. These thermal features are windows into the deep underground, places where we can actually touch water that has been heated by the same forces that drive plate tectonics and volcanic activity. The famous Old Faithful geyser in Yellowstone National Park is powered by a complex underground plumbing system where water descends deep into the earth, becomes superheated by underground volcanic activity, then erupts periodically when pressure builds up enough to overcome the weight of the water column above. The entire Yellowstone region sits atop a vast underground hot water system fed by magma chambers miles below the surface. Underground water also plays a crucial role in supporting surface ecosystems. Many rivers that appear to flow year-round are actually fed by underground springs and seepage from nearby aquifers. During dry periods, when surface runoff disappears, these underground sources maintain stream flow and provide water for wildlife and vegetation. The health of surface water bodies is intimately connected to the underground water systems that feed them. The scale of underground water movement becomes apparent when we consider that some groundwater systems span entire continents. The Great Artesian Basin in Australia covers nearly 1/4 of the continent, containing underground water that fell as rain in the mountains of eastern Australia and now flows slowly westward beneath the desert interior. Wells drilled into this system can produce water without pumping, as the pressure from water recharge areas hundreds of miles away is sufficient to push water to the surface. But underground water is not always fresh and drinkable. As water moves through rock formations, it dissolves minerals and can become highly saline or contaminated with naturally occurring chemicals. Some aquifers contain water so salty that it rivals the ocean, while others may contain naturally occurring arsenic, fluoride, or radioactive elements. The chemistry of groundwater tells the story of its journey through different rock formations, each leaving its chemical signature in the water. In coastal areas, underground fresh water often floats on top of heavier salt water that has intruded from the ocean. This creates a delicate balance where overpumping of fresh water wells can cause salt water to move upward and contaminate the freshwater supply. Many coastal communities must carefully manage their groundwater use to prevent this saltwater intrusion from destroying their water resources. The interaction between underground water and surface water creates some of the most productive ecosystems on Earth. Wetlands are often found where the water table intersects the surface, creating areas where underground water feeds surface vegetation year-round. These zones support incredibly diverse plant and animal communities and serve as critical habitat for countless species. Underground water also carves the landscape in ways that are not immediately obvious. Subsidence, the gradual sinking of land, often occurs when underground water is pumped out faster than it can be replenished. As the water leaves spaces in loose sediments, the sediments compact and the surface above sinks. Some areas of California's Central Valley have sunk more than 28 feet due to extensive groundwater pumping, creating problems for infrastructure and flood control. The study of underground water requires detective work that rivals any mystery novel. Hydrogeologists use a variety of tools to map underground water systems, from sensitive instruments that measure tiny variations in gravity caused by underground water to chemical tracers that can follow the path of water through rock formations. They analyze the age of groundwater using radioactive isotopes, sometimes discovering that water in deep aquifers fell as rain thousands of years ago during the last ice age. Modern technology has revealed that underground water systems are far more complex and interconnected than early scientists imagined. Satellite imagery can detect subtle changes in land elevation caused by seasonal variations in groundwater levels. Computer models now simulate the three-dimensional flow of underground water, helping scientists understand how these hidden systems respond to drought, climate change, and human activities. The discovery of underground water on other planets has added new excitement to the study of terrestrial groundwater systems. Mars appears to have extensive underground water ice, and some scientists believe liquid water may exist in underground aquifers on the red planet. Jupiter's moon Europa almost certainly has a vast underground ocean beneath its icy surface, while Saturn's moon Enceladus shoots geysers of underground water into space through cracks in its frozen crust. As we contemplate these hidden water systems beneath our feet, we begin to appreciate that Earth's underground realm is not a static, lifeless zone, but a dynamic, flowing world that connects distant places and spans vast timescales. The water flowing from your tap today may have begun its journey as rain falling on mountains hundreds of miles away and dozens of years ago. It has traveled through darkness, been filtered and purified by passage through sand and rock, and emerged to sustain life in ways both seen and unseen. The hidden waters beneath our feet remind us that our planet is an integrated system where surface and underground, near and far, present and past are all connected in an intricate web of relationships. Every drop of rain that falls, every stream that flows, every plant that grows is part of this grand circulation system that operates largely out of sight, but never out of influence on the world above. Life persists where light never reaches. As we venture deeper into the hidden world beneath our feet, we discover one of the most astonishing revelations of modern science. The Earth below us is not a sterile, lifeless realm, but a thriving biosphere that may contain more living organisms than exist on the entire surface of our planet. This is the deep biosphere, a shadow world of life that operates by rules entirely different from those governing the familiar ecosystems above ground. For most of human history, we believe that life required three basic ingredients: sunlight for energy, moderate temperatures, and liquid water. The world below ground was thought to be too dark, too hot, and too hostile for anything to survive. Yet in recent decades, scientists have discovered that this underground realm teems with an incredible diversity of microorganisms that have found ways to thrive in conditions that would instantly kill any surface-dwelling creature. The journey into the deep biosphere begins just below the soil surface, in the shallow depths where plant roots still penetrate and where some sunlight-derived energy can still reach. Here, in the first few feet of Earth, the microbial world is rich and diverse, filled with bacteria and fungi that decompose organic matter and cycle nutrients that feed the plants above. But this is just the beginning of life's underground kingdom. As we descend deeper, past the reach of plant roots and beyond the influence of surface organic matter, we encounter the first truly underground ecosystems. These are communities of microorganisms that have completely severed their dependence on the sun above. Instead of relying on photosynthesis, these deep-dwelling bacteria have evolved to extract energy from chemical reactions involving the rocks and minerals around them. At depths of hundreds of feet, where no trace of sunlight has ever penetrated, bacteria feed on sulfur compounds, iron minerals, and even radioactive elements. They live in a world of pure chemistry, breaking down and building up molecules in ways that would seem magical to surface dwellers. Some of these bacteria can survive in water hot enough to boil an egg, while others thrive in acidic conditions that would dissolve metal. The discovery of this deep life came gradually, often by accident. In the 1920s, oil drillers began noticing that their drilling equipment would sometimes become clogged with a slimy substance that seemed to be alive. At first dismissed as contamination from the surface, this material was eventually recognized as communities of bacteria living in the rock formations thousands of feet below ground. These organisms had been thriving in the darkness for millions of years, completely unknown to science. One of the most remarkable aspects of the deep biosphere is its sheer size and extent. Scientists now estimate that the total mass of microorganisms living beneath the surface may equal or exceed the mass of all life on Earth's surface. This hidden biomass exists in every conceivable underground environment, from the spaces between sand grains in aquifers to the tiny cracks in solid granite miles below the surface. The deepest confirmed life on Earth has been found at depths of over 3 miles below the surface, in gold mines in South Africa. Here, in crushing darkness and temperatures approaching 200 degrees Fahrenheit, bacteria continue to live and reproduce. The pressure at these depths is hundreds of times greater than at sea level, yet these organisms have adapted to call this extreme environment home. These deep-dwelling bacteria, known as extremophiles, have evolved incredible strategies for survival. Some can withstand radiation levels that would be fatal to any surface organism. Others can enter a state of suspended animation when conditions become too harsh, remaining dormant for millions of years until favorable conditions return. When scientists revived bacteria from rock samples that were over 250 million years old, they demonstrated that life in the deep can persist across geological timescales that dwarf human comprehension. The energy sources available to deep biosphere organisms are unlike anything we see on the surface. Instead of deriving energy from sunlight through photosynthesis, these bacteria practice chemosynthesis, a process that extracts energy from chemical reactions. Some feed on hydrogen gas seeping up from deeper in the earth. Others consume methane, ammonia, or sulfur compounds. Many can metabolize iron, manganese, or other metals, essentially eating the rocks around them. One particularly fascinating group of deep biosphere organisms survives by splitting water molecules and feeding on the hydrogen released in the process. This radiolysis is caused by natural radioactivity in the surrounding rocks, which breaks apart water molecules and provides a steady source of chemical energy. In effect, these bacteria are powered by the natural radioactive decay of uranium and other elements in Earth's crust, making them some of the most exotic life forms on our planet. The deep biosphere also includes more complex organisms than just bacteria. Scientists have discovered viruses, archaea, and even some simple eukaryotic cells living in underground environments. Some deep aquifers contain communities of organisms that include multiple species interacting in complex food webs, even though the entire ecosystem exists in complete darkness and relies entirely on chemical energy sources. The metabolic rates of deep biosphere organisms are incredibly slow compared to surface life. Where surface bacteria might reproduce every 20 minutes under ideal conditions, deep biosphere bacteria may take months, years, or even decades to complete a single reproductive cycle. They exist in a state of extremely slow motion, where biological processes that happen quickly on the surface unfold with geological patience. This slow pace of life in the deep has profound implications for how we understand biological timescales. Some individual bacteria in the deep biosphere may be thousands of years old, having lived through entire civilizations of human history. They represent a form of life that bridges the gap between biological and geological time, organisms whose individual lifespans can span millennia. The chemical processes carried out by deep biosphere organisms have a significant impact on the geology and chemistry of our planet. These bacteria can precipitate minerals, alter rock formations, and influence the movement of groundwater. They play crucial roles in global cycles of carbon, sulfur, nitrogen, and other elements, acting as living chemical processes that modify the composition of deep Earth materials. Some deep biosphere bacteria produce methane as a waste product of their metabolism. This biological methane can migrate upward through rock formations and contribute to natural gas deposits found in sedimentary rocks. In some cases, what we extract as fossil fuel may actually be the product of ongoing biological processes happening miles below our feet. The discovery of the deep biosphere has revolutionized our understanding of the limits of life. Organisms have been found living in environments previously thought to be completely sterile, from the interior of solid rock to the highly saline waters of deep aquifers. The temperature limits for life keep being pushed higher as scientists discover bacteria thriving in increasingly hot environments deep underground. Pressure, which was once thought to be a limiting factor for life, has proven to be less of a barrier than expected. Deep biosphere organisms have evolved cellular mechanisms that allow them to function normally under crushing pressure that would destroy surface life. Their cell walls and internal structures are specially adapted to maintain integrity and function in high-pressure environments. The isolation of deep biosphere communities has led to remarkable evolutionary developments. Cut off from surface ecosystems for millions of years, some deep bacteria have evolved unique metabolic pathways found nowhere else on Earth. They represent independent experiments in evolution, showing how life can adapt to extreme conditions when given enough time. One of the most intriguing aspects of deep biosphere research is its implications for the search for life on other planets. If life can thrive in the extreme conditions found miles below Earth's surface, it suggests that similar organisms might exist in the subsurface environments of Mars, Europa, Enceladus, and other worlds in our solar system. The deep biosphere provides a template for how life might persist in harsh planetary environments. The study of deep biosphere organisms has also provided insights into the early evolution of life on Earth. Many deep-dwelling bacteria use metabolic pathways that may be similar to those employed by the earliest life forms on our planet, before oxygen became abundant in the atmosphere. These modern extremophiles may be living representatives of ancient lifestyles that dominated Earth billions of years ago. Researchers studying the deep biosphere use sophisticated drilling techniques to obtain samples from great depths while avoiding contamination from surface organisms. Special drilling fluids and sterile sampling procedures ensure that the microorganisms they study actually come from the deep underground rather than being carried down from the surface during drilling operations. The genetic analysis of deep biosphere organisms has revealed an incredible diversity of life forms. Many of these bacteria are so different from surface organisms that they represent entirely new branches on the tree of life. Some are more closely related to each other than to any surface-dwelling species, suggesting that they have been evolving independently in the deep for hundreds of millions of years. The deep biosphere also plays important roles in the cycling of elements between Earth's surface and interior. Deep-dwelling bacteria can transport carbon, nitrogen, sulfur, and other elements from surface environments down into deep rock formations, or conversely, can bring deep Earth materials toward the surface through their metabolic activities. They serve as biological pumps that move materials between different reserves of our planet. Some deep biosphere organisms have developed symbiotic relationships with each other, creating complex ecological networks in the darkness. One species might produce waste products that serve as food for another, creating interconnected food webs that can sustain themselves indefinitely without any input from the surface. These underground ecosystems demonstrate that life can create its own closed loops of energy and material cycling. The discovery of life at ever greater depths continues to surprise scientists. Every new deep drilling project seems to find organisms living even deeper than previously thought possible. The current record holders are bacteria found at depths approaching 4 miles below the surface, but there is no clear indication that we have reached the absolute limits of the deep biosphere. Temperature appears to be the most significant limiting factor for deep life. As we go deeper into the Earth, temperatures eventually reach levels that denature proteins and break down the complex molecules that life requires. The current temperature limit for known life is around 250 degrees Fahrenheit, though some scientists speculate that specially adapted organisms might survive at even higher temperatures. The timescales involved in deep biosphere research are staggering. Some experiments designed to study the growth rates of deep bacteria require decades to complete. Scientists must plan studies that may outlast their own careers, passing research projects from one generation of researchers to the next. This long-term perspective matches the slow pace of life in the deep, where changes happen gradually over geological time. The deep biosphere represents a vast reservoir of genetic diversity that we are only beginning to explore. Many of the organisms living in these depths have unique enzymes and metabolic capabilities that could have important applications in biotechnology, medicine, and environmental cleanup. These extremophiles may hold keys to developing new industrial processes, treating pollution, or creating materials that can function under extreme conditions. As we contemplate the vast scope of the deep biosphere, we realize that our planet's living systems extend far beyond the thin skin of surface ecosystems that we can see. The earth beneath our feet is alive in ways that challenge our most basic assumptions about the nature and limits of life. In the crushing darkness miles below, countless organisms continue their slow dance of survival, reproduction, and evolution, creating a hidden biosphere that may be as complex and diverse as the familiar world above. The deep biosphere reminds us that life is far more adaptable and persistent than we ever imagined. It shows us that our planet is alive not just on its surface, but throughout its depths, harboring forms of life so alien that they seem to come from another world, yet so fundamental that they may represent the most ancient and enduring expressions of life on Earth. In silent caves, strange creatures live in shadows. As we descend further into the hidden world beneath our feet, we enter one of the most mysterious and beautiful realms on Earth, the world of caves and underground spaces. These are not merely empty holes in the rock, but vibrant ecosystems filled with life forms so uniquely adapted to darkness that they seem to belong to another planet entirely. The formation of caves is a story written in water and time, a process so gradual that it spans millions of years, yet so persistent that it can carve cathedral-sized chambers from solid rock. Most caves begin their existence when slightly acidic water, enriched with carbon dioxide from the atmosphere and soil above, encounters limestone or other soluble rock formations. This weak acid, no stronger than the carbonation in a soft drink, begins the patient work of dissolution that will eventually create vast underground galleries. Picture a single drop of rainwater as it begins this incredible journey. It falls from the sky, absorbs carbon dioxide as it passes through the atmosphere, then gains even more acidity as it filters through soil rich with organic matter. When this humble drop encounters limestone, it begins a chemical reaction that dissolves tiny amounts of the rock. Multiplied by billions of drops over millions of years, this simple process carves out some of the most spectacular landscapes on Earth. The process begins with the formation of tiny cracks and fissures in the rock. Water follows these weak points, gradually enlarging them through constant chemical erosion. Over thousands of years, these hairline fractures grow into tunnels, and the tunnels expand into rooms. The largest cave chambers are testimony to the incredible power of patient, persistent dissolution, creating spaces so vast that entire city blocks could fit within their walls. Mammoth Cave in Kentucky, the longest known cave system in the world, stretches for over 400 miles of mapped passages. This underground labyrinth has been carved by water flowing through limestone layers for millions of years, creating a three-dimensional maze that extends far beyond what any single human could explore in a lifetime. The cave system is so extensive that new passages are still being discovered regularly, adding to its already record-breaking length. But caves are far more than empty spaces carved by water. They are complex ecosystems that support an astonishing variety of life forms, many of which exist nowhere else on Earth. The complete absence of sunlight has driven evolution in directions that would seem impossible to surface dwellers, creating creatures so perfectly adapted to darkness that they represent some of the most extreme examples of evolutionary specialization known to science. The journey into a cave ecosystem begins at the entrance, where twilight gives way to eternal darkness. This zone, called the entrance zone, still receives some indirect sunlight and experiences temperature fluctuations from the outside world. Here, live creatures that can survive in both light and dark conditions, animals that venture out to the surface world at night, but retreat to the safety of the cave during the day. As we move deeper into the cave, we enter the twilight zone, where the last traces of natural light fade away. The temperature becomes constant year-round, typically matching the average annual temperature of the region above. In this zone, we encounter the first truly cave-adapted creatures, animals that have begun to lose their dependence on the surface world and have started down the evolutionary path toward permanent cave dwelling. Beyond the twilight zone lies the dark zone, a realm of eternal night where no trace of sunlight has ever penetrated. Here, in temperatures that rarely vary by more than a few degrees throughout the year, live some of the most remarkable creatures on Earth. These are the troglobites, animals so completely adapted to cave life that they cannot survive in the outside world. The evolutionary changes that allow animals to thrive in caves are both dramatic and subtle. The most obvious adaptation is the loss of eyes and pigmentation. In a world where light never penetrates, eyes become not just useless but actually costly to maintain. Over thousands of generations, cave-dwelling animals gradually lose their sight, often retaining only light-sensitive spots or completely eyeless heads where their ancestors once had complex visual organs. The loss of pigmentation follows a similar pattern. In the surface world, skin and fur colors serve important functions in communication, camouflage, and protection from ultraviolet radiation. But in the eternal darkness of caves, these pigments become unnecessary metabolic expenses. Cave-adapted animals often appear ghostly white or translucent, their skin so pale that blood vessels show through, like delicate tracery. But evolution in caves is not just about losing unnecessary features. Cave animals have also evolved enhanced senses to replace their lost vision. Many have developed extraordinarily sensitive hearing, able to navigate and hunt using sound in ways that would seem supernatural to surface animals. Others have evolved enhanced senses of touch, with elongated antennae, whiskers, or other sensory organs that can detect the slightest air movements or vibrations. The olm, a cave-dwelling salamander found in southeastern Europe, represents one of the most extreme examples of cave adaptation. These pale, almost translucent creatures are completely blind and can live for over 100 years. They have evolved such a slow metabolism that they can survive without food for up to 10 years, an adaptation that allows them to thrive in an environment where food sources are scarce and unpredictable. Cave ecosystems operate on fundamentally different principles than surface ecosystems. Without photosynthesis to provide energy, cave communities depend entirely on organic matter that filters down from the surface world. This might include leaf litter washed in by underground streams, organic debris carried in by bats, or nutrients dissolved in groundwater. The scarcity of food in caves has led to the evolution of incredibly efficient recycling systems where every scrap of organic matter is utilized multiple times by different organisms. Bats play a crucial role in many cave ecosystems, serving as living links between the surface and underground worlds. Millions of bats roost in caves during the day, then venture out at night to feed in surface environments. When they return to their cave roosts, they bring energy from the outside world in the form of guano, which supports entire underground food webs. Some caves contain guano deposits many feet deep, accumulated over thousands of years of bat occupation. The guano piles in bat caves are ecosystems unto themselves, supporting communities of specialized bacteria, fungi, insects, and other invertebrates. These organisms break down the bat droppings and make the nutrients available to other cave dwellers. Some caves have such rich guano deposits that they were historically mined for fertilizer, testament to the incredible productivity that can result from this connection between surface and underground ecosystems. Cave streams and underground rivers create their own unique habitats within the larger cave ecosystem. These waterways often contain fish species found nowhere else on Earth, many of them blind and colorless like other cave-adapted animals. The Mexican tetra, a fish that exists in both surface and cave-dwelling forms, has become a model organism for studying the genetic changes that accompany adaptation to cave life. The constant temperature and humidity of caves create microclimates that can preserve delicate formations and artifacts for incredibly long periods. Some caves contain fossils, ancient artwork, or archaeological remains that have been perfectly preserved by the stable underground environment. These caves serve as natural museums, protecting treasures from the past that would have been destroyed long ago if exposed to surface weathering. Cave formations themselves are among the most beautiful and intricate natural sculptures on Earth. Stalactites hanging from cave ceilings and stalagmites rising from cave floors are created by the same chemical processes that carved the caves, but working in reverse. As water laden with dissolved minerals drips from the ceiling, it leaves behind tiny deposits of calcite or other minerals. Over thousands of years, these deposits accumulate into the graceful formations that make some caves look like natural cathedrals. The variety of cave formations seems almost limitless. Flowstone creates cascading sheets of mineral deposits that look like frozen waterfalls. Cave pearls form in pools where dripping water causes small particles to roll around, gradually accumulating layers of minerals like natural ball bearings. Soda straws are delicate, hollow stalactites that can grow to remarkable lengths while remaining as thin as drinking straws. Some caves contain formations so delicate and intricate that they seem more like artwork than geology. Cave flowers are crystalline formations that bloom from cave walls in impossible defiance of gravity. Gypsum formations can create underground gardens of crystal flowers so fragile that the breath of a visitor can damage them permanently. The discovery and exploration of caves has always captured human imagination. Cave art dating back tens of thousands of years shows that our ancestors were drawn to these underground spaces, using them for shelter, ceremony, and artistic expression. The paintings in caves like Lascaux and Altamira represent some of humanity's earliest artistic achievements, preserved in the stable environment of cave chambers for millennia. Modern cave exploration, called speleology, has revealed underground worlds of incredible complexity and beauty. Explorers using advanced techniques have mapped cave systems that extend for hundreds of miles, discovered underground rivers larger than surface streams, and found chambers so large that weather systems can form inside them. The big room in Carlsbad Caverns could hold 14 football fields on its floor, with a ceiling high enough to accommodate a 30-story building. The study of cave ecosystems has provided insights into evolution, ecology, and the limits of life that extend far beyond the underground world. Cave organisms have evolved solutions to problems of food scarcity, sensory navigation, and energy conservation that have applications in fields ranging from robotics to medicine. The ability of some cave animals to survive with minimal food intake for extended periods is being studied for its potential applications in space exploration and medical treatments. Caves also serve as natural laboratories for studying climate change and environmental variation. Because cave environments are buffered from surface weather, they preserve records of past climate conditions in their formations and sediments. Ice caves contain ice deposits that can preserve atmospheric gases from thousands of years ago, providing scientists with direct samples of ancient air. The hydrology of cave systems plays important roles in regional water supplies and flood control. Many cave systems serve as natural underground reservoirs, storing water during wet periods and releasing it slowly during droughts. Understanding cave hydrology is crucial for managing water resources in regions where underground water flow through cave systems significantly affects surface water availability. Unfortunately, cave ecosystems are among the most vulnerable environments on Earth. Because they depend on inputs from surface ecosystems and are isolated from each other, cave communities can be easily disrupted by changes in land use, water pollution, or climate variations above ground. Many cave-adapted species exist in only a single cave system, making them extremely vulnerable to extinction from disturbances. The conservation of cave ecosystems requires understanding the connections between surface and underground environments. Protecting a cave species often means protecting the entire watershed above the cave, since pollution or habitat destruction on the surface can filter down to affect underground communities. This highlights the interconnected nature of surface and subsurface environments, reminding us that the hidden world below is intimately connected to the visible world above. As we explore these underground galleries and contemplate the remarkable creatures that call them home, we gain a new appreciation for the diversity and adaptability of life on Earth. Caves represent some of the most extreme environments on our planet, yet they support thriving ecosystems that have persisted for millions of years. They remind us that life finds a way to flourish even in the most unlikely places, creating beauty and complexity in realms where we might least expect them. The silent world of caves speaks to us of deep time, patient processes, and the incredible creativity of evolution. In these underground cathedrals, carved by water and inhabited by creatures of shadow, we discover that our planet holds wonders that rival anything in our imagination, hidden just beneath our feet in chambers of eternal night. Science pushes boundaries, but mysteries remain deep. As we journey deeper into the hidden world beneath our feet, we encounter one of the most persistent and fascinating chapters in human imagination: the idea that our planet might contain vast hollow spaces, perhaps even entire worlds hidden within its depths. While modern science has revealed much about Earth's true structure, the allure of unknown realms continues to capture our imagination and drive us to explore the limits of what might be possible in the deep underground. The concept of a hollow Earth has ancient roots, appearing in mythologies and stories from cultures around the world. Long before we had any scientific understanding of our planet's interior, humans imagined vast caverns and underground kingdoms existing beneath their feet. These weren't merely flights of fancy, but attempts to explain the mysterious phenomena they observed. earthquakes that shook the ground, volcanic eruptions that brought molten rock from unknown depths, and deep caves that seemed to extend infinitely into darkness. In Greek mythology, the underworld of Hades was described as a vast realm beneath the surface world, complete with rivers, landscapes, and cities. Hindu cosmology spoke of multiple layers of reality existing below the surface of the earth, each with its own inhabitants and characteristics. Norse mythology described underground realms connected to the surface world through roots of the Great World Tree. These ancient stories reflect a deep human intuition that the earth beneath us holds secrets and spaces far greater than what we can see. The modern scientific exploration of hollow earth theories began in the 17th century, when mathematician and astronomer Edmund Halley, famous for the comet that bears his name, proposed that Earth might consist of concentric spheres, one inside the other, with vast spaces between them. Halley's theory was an attempt to explain the behavior of magnetic compasses, which sometimes pointed in unexpected directions. He suggested that these magnetic anomalies might be caused by separate magnetic fields generated by the inner spheres. Halley's ideas were expanded upon by other scientists and writers throughout the 18th and 19th centuries. Some proposed that these inner worlds might be inhabited, heated by internal suns, and accessible through openings at the north and south poles. The theory gained enough credibility that several expeditions were actually mounted to search for these polar openings, though none ever found the entrances to inner worlds that the theories predicted. One of the most influential proponents of hollow earth theory was John Cleve Sims, an American Army officer who spent years in the early 1800s promoting his belief that Earth was hollow and habitable within. Sims proposed that there were openings at both poles, each about 4,000 miles in diameter, leading to the interior world. He petitioned the United States government to fund an expedition to find these openings, and though he never received official support, his ideas inspired numerous books, articles, and even fictional works. The hollow earth concept reached its peak of popular acceptance in the mid-1800s, when it captured the imagination of writers and explorers alike. Jules Verne's famous novel Journey to the Center of the Earth popularized the idea of vast underground spaces filled with prehistoric creatures and hidden wonders. While Verne presented his story as fiction, it reflected the genuine scientific curiosity of the time about what might exist in Earth's unexplored depths. As scientific understanding of geology and physics advanced, the hollow earth theories began to face serious challenges. The development of seismology in the late 1800s and early 1900s provided the first direct evidence about Earth's internal structure. When earthquakes send shock waves through the planet, these waves travel at different speeds through different materials, allowing scientists to map the density and composition of Earth's interior layers. The seismic evidence was clear and undeniable. Earth is not hollow, but consists of distinct layers of increasing density toward the center. The discovery of Earth's liquid outer core and solid inner core, revealed through careful analysis of earthquake waves, definitively refuted the idea of vast hollow spaces in our planet's interior. The immense pressures that exist at depth would crush any large cavities, making hollow Earth theories physically impossible under our current understanding of physics and geology. Yet even as mainstream science moved away from hollow Earth theories, the concept continued to evolve and find new expressions. Some modern proponents have suggested that while Earth as a whole is not hollow, it might contain extensive networks of natural caverns, far larger than any we have discovered. They point to the fact that we have directly explored only a tiny fraction of our planet's subsurface, leaving vast volumes of underground space still unknown to science. The possibility of undiscovered large underground spaces is not entirely without merit from a scientific perspective. We know that cave systems can extend for hundreds of miles, and new discoveries regularly reveal underground chambers of surprising size. The deepest mines and drill holes have penetrated only a few miles into Earth's crust, leaving the vast majority of the subsurface unexplored by direct human investigation. Some scientists have speculated about the theoretical maximum size of underground caverns that could exist within Earth's crust. While the crushing pressure at great depths would collapse most large open spaces, certain geological conditions might allow for the formation of substantial underground voids. Lava tubes created by ancient volcanic activity could potentially extend for great distances underground. Salt domes and other geological formations might create large underground spaces under specific conditions. the discovery of increasingly large underground features continues to surprise scientists. Recent explorations have revealed underground rivers, systems that dwarf surface rivers, cave chambers large enough to hold entire city blocks, and interconnected cave networks that span hundreds of miles. Each new discovery pushes the boundaries of what we thought possible in terms of underground space and complexity. In Vietnam, the Son Tra cave system contains chambers so large that they could accommodate entire city blocks. The largest chamber, known as Hang Son Doong, is over 3 miles long, contains sections 600 feet wide and 400 feet tall, and includes its own underground rivers and jungle ecosystems. The discovery of such enormous natural spaces reminds us that Earth's underground realm still holds surprises that challenge our assumptions about what is possible beneath the surface. The search for unknown underground realms has been aided by advancing technology that allows us to peer deeper into Earth's interior without physically excavating. Ground-penetrating radar, gravitational anomaly detection, and sophisticated seismic analysis have revealed underground structures and spaces that were previously undetectable. These techniques have uncovered hidden chambers beneath known archaeological sites, located underground water reservoirs in arid regions, and mapped complex cave systems without the need for direct exploration. Satellite technology has also contributed to the search for underground mysteries. Subtle changes in Earth's gravitational field, detectable by sensitive satellite instruments, can indicate the presence of underground spaces or density variations that might suggest hidden caverns or geological structures. These space-based detection methods have revealed underground features spanning continental scales, including ancient underground river systems and vast groundwater reservoirs. The concept of unknown underground realms has found new relevance in the search for life on other planets. Scientists studying Mars have discovered evidence of extensive underground spaces that might once have harbored water and possibly life. Some of these Martian underground features appear to be lava tubes large enough to contain entire cities, leading to speculation about their potential as shelters for future human explorers or as refuges where Martian life might still exist. On Earth, the discovery of extremophile organisms in deep underground environments has expanded our understanding of where life might exist within our planet. If complex ecosystems can thrive in the harsh conditions found miles below the surface, it raises questions about what other unknown biological communities might exist in underground spaces we have yet to discover. The deep biosphere continues to reveal new forms of life in places we never expected, suggesting that Earth's underground realm may harbor biological surprises as dramatic as any geographical discoveries. The theoretical physics of large underground spaces presents fascinating challenges and possibilities. While solid rock cannot support truly enormous caverns at great depths due to pressure, certain conditions might allow for substantial open spaces under specific circumstances. Underground chambers filled with gas under pressure, spaces supported by unique geological formations, or caverns maintained by ongoing geological processes might exist under conditions we have not yet encountered or fully understood. Some researchers have proposed that Earth's interior might contain pockets of different composition or structure that could support larger spaces than conventional geology would predict. These might include regions where gas pressure counteracts crushing forces, areas where unique mineral formations provide exceptional structural support, or zones where ongoing geological activity maintains open spaces against the tendency toward collapse. The study of impact craters has revealed that massive asteroid or comet impacts can create underground structures of enormous scale. Some impact events may have created underground spaces or altered subsurface geology in ways that could allow for the formation of large caverns or connected underground systems. The Chicxulub impact that contributed to the extinction of the dinosaurs created underground shock formations that extend for hundreds of miles, demonstrating that planetary-scale events can modify Earth's subsurface structure in dramatic and lasting ways. Advanced computer modeling now allows scientists to simulate the formation and stability of large underground spaces under various geological conditions. These models suggest that while traditional hollow Earth theories are impossible, certain combinations of geological factors might allow for underground chambers or connected spaces significantly larger than any we have discovered. The models also help identify the conditions under which such spaces might form and where they would be most likely to exist. The search for unknown underground realms continues to motivate exploration and scientific research. Deep drilling projects push ever deeper into Earth's crust, each new depth record potentially revealing previously unknown underground features or conditions. Ocean floor drilling has discovered underground chambers and water systems beneath the seafloor that challenge our understanding of subsurface hydrology and geology. Cave exploration continues to reveal new underground spaces and connections that expand known cave systems. The use of underwater robots and remote sensing equipment allows explorers to map underwater cave systems and underground rivers that were previously inaccessible. Each new discovery adds to our understanding of just how extensive and complex Earth's underground realm can be. The concept of unknown underground realms also intersects with our understanding of Earth's geological history. Ancient impact events, massive volcanic eruptions, and other geological catastrophes may have created underground structures that persist today in forms we do not yet recognize. The geological record suggests that Earth has experienced events of such magnitude that they could have fundamentally altered subsurface structure in ways that might still be detectable. As we contemplate the possibility of unknown realms beneath our feet, we are reminded that Earth still holds mysteries that challenge our understanding and capture our imagination. While the classical hollow Earth theories have been definitively refuted by modern science, the quest to understand what lies beneath us continues to reveal wonders that rival any fiction. The underground world remains a frontier where new discoveries regularly surprise us and push the boundaries of what we thought possible. The enduring appeal of hollow Earth and underground realm theories speaks to something fundamental in human nature: our desire to believe that there are still unknown places left to discover, still mysteries left to solve. In an age when satellite imagery can map Earth's surface in extraordinary detail, the underground realm remains largely unknown, holding the promise that genuine surprises and discoveries still await us in the hidden world beneath our feet. Perhaps the greatest mystery is not whether vast hollow spaces exist within our planet, but what other wonders the underground realm might contain that we have not yet imagined. Each new discovery in the deep underground reveals that Earth's hidden world is far more complex, extensive, and surprising than we ever expected, ensuring that the quest to understand what lies beneath us will continue to challenge and inspire future generations of explorers and scientists. We reach deeper, unlocking the planet's secrets one layer at a time. Throughout human history, our curiosity about what lies beneath our feet has driven us to dig deeper, drill further, and explore more extensively into the hidden realm below. This quest to understand and access the deep Earth has pushed the boundaries of human engineering, revealed fundamental secrets about our planet, and continues to challenge us with technical problems that test the limits of our technology and determination. The human journey into the deep Earth began with the simplest of tools and the most basic of needs. Our earliest ancestors dug into the ground to find water, to create shelter, and to extract useful materials like clay and stone. These modest excavations, rarely more than a few feet deep, represented humanity's first tentative steps into the underground world. From these humble beginnings grew an ever-expanding quest to reach deeper into our planet's interior. The development of mining marked a crucial turning point in human exploration of the deep Earth. As civilizations discovered valuable metals and minerals beneath the surface, they began digging shafts and tunnels that extended far below ground level. Ancient copper mines in the Great Lakes region of North America reached depths of over 70 feet, impressive achievements using only simple stone and wooden tools. These early miners worked by firelight in cramped, dangerous conditions, slowly expanding human presence into the underground realm. The Bronze Age and Iron Age brought more sophisticated mining techniques and deeper excavations. Ancient civilizations developed methods for following mineral veins deep into hillsides and mountains, creating elaborate underground networks that could extend for miles. Roman engineers became particularly skilled at underground construction, building extensive aqueduct systems that included long tunnels through solid rock and creating mines that reached depths previously thought impossible. The Industrial Revolution transformed human ability to explore the deep Earth. Steam-powered pumps allowed miners to work in flooded areas and reach greater depths. Steam-powered machinery could move earth and rock far more efficiently than human muscle power alone. The development of dynamite and other explosives made it possible to blast through hard rock formations that had previously been impenetrable barriers to deeper exploration. As mining operations reached greater depths, they encountered new challenges that pushed the boundaries of engineering knowledge. Underground temperatures increased with depth, making working conditions increasingly difficult. Water seepage became a constant problem, requiring ever more powerful pumping systems. The pressure from surrounding rock created structural challenges that required new techniques in tunnel construction and support. The deepest mines in the world today represent the current limits of human penetration into the earth. Gold mines in South Africa extend more than 2.5 miles below the surface, reaching depths where the temperature of the surrounding rock approaches 130 degrees Fahrenheit. These mines require massive cooling systems to make working conditions bearable, with underground air conditioning plants that rival those of large buildings on the surface. Working at such depths presents unique challenges that test human endurance and engineering skills. The journey to the bottom of the deepest mines can take over an hour in high-speed elevators, descending through shaft systems that extend deeper than most mountains at all. The pressure at these depths is so great that the rock itself flows slowly like thick liquid, requiring constant maintenance of tunnels and support structures. The development of scientific drilling has opened new frontiers in deep earth exploration. Unlike mining, which seeks to extract valuable materials, scientific drilling aims to understand the structure and composition of our planet's interior. These projects push drilling technology to its absolute limits, seeking to reach depths that no human will ever visit in person, but from which we can extract invaluable scientific information. The Soviet Union's Kola Superdeep Borehole project, begun in 1970, represents one of the most ambitious attempts to drill as deeply as possible into Earth's crust. The project aimed to drill 9 miles down, deeper than anyone had ever attempted. Although the drill never reached its target depth, it did achieve a record of over 7.5 miles, deeper than the height of Mount Everest. The Kola project revealed unexpected discoveries about conditions in the deep earth. Scientists expected to find dry rock at great depths, but instead encountered wet conditions, with water existing much deeper than theory predicted. The temperatures at depth were also higher than expected, reaching over 350 degrees Fahrenheit instead of the predicted 200 degrees. These findings forced scientists to revise their understanding of deep Earth conditions and highlighted how much we still don't know about our planet's interior. The technical challenges of drilling to extreme depths are immense. As drill bits penetrate deeper, they encounter increasing temperatures and pressures that can destroy conventional drilling equipment. The drill string itself, the long series of connected pipes that carries the drill bit, becomes so heavy at great depths that its own weight threatens to break the connection. Keeping the hole open as drilling progresses requires sophisticated engineering to prevent collapse from the surrounding rock pressure. Modern deep drilling projects use advanced materials and techniques developed specifically for extreme conditions. Diamond-tipped drill bits can cut through the hardest rocks. Special drilling fluids help cool the equipment and carry rock debris to the surface. Computer-controlled systems monitor drilling conditions in real time and adjust operations to maintain optimal performance under challenging conditions. Ocean drilling has opened another frontier in deep Earth exploration. Ships equipped with sophisticated drilling equipment can access the ocean floor and drill into the sediments and rocks beneath. The ocean drilling program has recovered core samples from locations around the world, providing insights into Earth's history, climate change, and geological processes that would be impossible to obtain any other way. Deep ocean drilling faces unique challenges beyond those encountered on land. The drilling ship must maintain precise position above the drill site, despite ocean currents and weather conditions. The drill string must extend through thousands of feet of water before even reaching the seafloor. Remote-operated vehicles and other underwater technologies are essential for monitoring and maintaining drilling operations in the deep ocean environment. Some of the most important scientific discoveries about Earth's interior have come from analysis of core samples retrieved by deep drilling projects. These cylindrical sections of rock, extracted from deep within the Earth, provide direct physical evidence of conditions and processes that existed millions of years ago. The cores contain fossilized remains of ancient life, records of past climate conditions, and evidence of geological events that shaped our planet. The analysis of drill cores requires sophisticated laboratory techniques to extract maximum information from these precious samples. Scientists can determine the age of rock layers using radioactive dating methods, analyze the chemical composition to understand past environmental conditions, and study microscopic fossils to learn about ancient ecosystems. Each core sample is like a book written in stone, containing chapters of Earth's history that can be read by those with the knowledge to interpret the evidence. Future deep Earth exploration projects are being planned that will push even deeper into our planet's interior. Advanced drilling techniques using laser technology, improved materials that can withstand extreme conditions, and robotic systems that can operate autonomously in deep underground environments may allow us to reach depths previously thought impossible. Some proposals envision drilling projects that could reach the boundary between Earth's crust and mantle, providing direct access to materials from deep within our planet. The exploration of deep Earth environments has also driven the development of technologies that have applications far beyond geology and mining. High-pressure, high-temperature materials developed for deep drilling have found uses in aerospace, electronics, and medical equipment. Remote sensing and robotic technologies developed for underground exploration have contributed to advances in space exploration, underwater research, and hazardous environment operations. Underground laboratories built in deep mines have become important facilities for scientific research that requires isolation from cosmic radiation and other surface interference. These deep underground facilities provide ideal conditions for experiments in particle physics, the search for dark matter, and other fundamental research that requires the shielding provided by thousands of feet of rock overhead. The construction of underground facilities for scientific research represents another form of deep Earth exploration. Creating laboratory spaces deep underground requires solving complex engineering problems related to ventilation, structural support, and access in challenging environments. These facilities demonstrate human ability to create functional spaces in the deep underground and suggest possibilities for future underground construction projects. Geothermal energy development has driven new forms of deep Earth exploration, focused on accessing the heat stored within our planet. Enhanced geothermal systems involve drilling deep wells and using advanced techniques to extract heat from hot, dry rock formations. These projects require drilling to depths of several miles and creating artificial underground heat exchange systems that can provide renewable energy for surface applications. The development of underground storage facilities has created new reasons for deep Earth exploration. Underground caverns and mines are being used to store everything from natural gas and petroleum products to nuclear waste and important cultural artifacts. Creating these storage facilities requires detailed understanding of underground geology and hydrology to ensure long-term stability and security. Space exploration has provided new perspectives on deep Earth exploration by allowing us to study the interiors of other planets and moons. Seismic instruments placed on the Moon and Mars have revealed information about their internal structure, while spacecraft have used gravitational measurements and other remote sensing techniques to map subsurface features on various worlds throughout the solar system. The search for life in extreme environments has driven exploration of some of the deepest and most challenging underground locations on Earth. Scientists studying extremophile organisms have descended into deep mines, underwater caves, and other subsurface environments to search for life forms that might provide clues about the possibility of life on other planets or in other extreme environments. As we contemplate the current state of human exploration of the deep Earth, we realize that despite centuries of digging, drilling, and excavation, we have barely scratched the surface of our planet's interior. The deepest mines and drill holes represent tiny pinpricks into Earth's vast interior, penetrating less than 1% of the distance to our planet's center. The underground realm remains largely unexplored, holding secrets and possibilities that will challenge future generations of explorers and scientists. The quest to explore deeper into the Earth continues to drive technological innovation and scientific discovery. Each new depth record achieved, each new core sample recovered, and each new underground facility constructed adds to our understanding of the hidden world beneath our feet. The challenges are immense, the costs are substantial, and the technical difficulties continue to test the limits of human capability. But the rewards in terms of scientific knowledge and practical applications make the effort worthwhile. The exploration of the deep Earth reminds us that our planet still holds frontiers, as challenging and mysterious as any found in the depths of space. While we have sent spacecraft to the edge of the solar system and observed galaxies billions of light years away, the interior of our own planet remains largely unknown, waiting for future explorers to unlock its secrets layer by layer, mile by mile, discovery by discovery. Beneath us, Earth breathes and sustains. As we delve deeper into understanding the hidden world below our feet, we discover that the underground realm is not simply a passive foundation for surface life, but an active participant in the grand cycles that regulate our planet's climate and sustain all living things. The subterranean world operates as Earth's circulatory system, moving energy, water, and essential elements in patterns that span continents and geological ages. The relationship between the underground world and Earth's climate begins with one of the most fundamental cycles on our planet, the carbon cycle. Deep beneath the surface, vast quantities of carbon are stored in rock formations, underground water systems, and the deep biosphere. This underground carbon reservoir dwarfs all the carbon in Earth's atmosphere, oceans, and surface life combined, making the subterranean world a crucial player in regulating global climate patterns. Underground carbon exists in many forms, each playing a different role in Earth's climate system. Limestone and other carbonate rocks contain enormous amounts of carbon that was once part of ancient marine organisms. Over millions of years, the remains of countless sea creatures accumulated on ocean floors, eventually becoming compressed into rock formations that now store carbon deep within Earth's crust. These underground carbon stores represent one of the largest reservoirs of carbon on our planet. When underground water comes into contact with carbonate rocks, it slowly dissolves them, releasing carbon dioxide that can eventually reach the atmosphere. This process, called chemical weathering, operates on geological timescales, but has profound effects on global climate over millions of years. During periods when underground water flow increases, more carbon dioxide is released from underground storage, potentially warming global climate. When underground water flow decreases, less carbon is released, allowing atmospheric carbon dioxide levels to drop. The deep biosphere also plays a crucial role in underground carbon cycling. Deep-dwelling bacteria and other microorganisms continuously process carbon-containing compounds, sometimes consuming carbon dioxide and sometimes producing it. These biological processes operate much more slowly than surface biological activity, but their cumulative effect over vast underground volumes can significantly influence global carbon budgets. Volcanic activity provides another crucial link between underground carbon storage and surface climate. When magma rises from deep within Earth, it often carries carbon dioxide that was stored in underground rock formations. Volcanic eruptions release this deep carbon directly into the atmosphere, where it can influence global climate patterns. Some of the largest climate changes in Earth's history have been triggered by massive volcanic events that released enormous quantities of underground carbon into the atmosphere. The underground world also regulates Earth's water cycle in ways that profoundly affect surface climate and weather patterns. Groundwater systems store and transport water across vast distances and timescales, creating climate effects that extend far beyond local weather patterns. During droughts, groundwater provides the water that keeps rivers flowing and vegetation alive. During floods, underground storage absorbs excess water that might otherwise cause more severe surface flooding. The thermal properties of the underground world create another important connection to Earth's climate system. The ground beneath our feet acts as a massive thermal reservoir, storing heat during warm periods and releasing it during cool periods. This underground thermal inertia helps moderate surface temperature swings and influences local and regional climate patterns. In winter, heat stored in the ground helps keep soil temperatures above freezing, even when air temperatures drop well below zero. Geothermal energy from Earth's interior provides a constant flow of heat toward the surface that affects climate in subtle but important ways. This underground heat drives many of the geological processes that shape Earth's surface, from the movement of tectonic plates to the creation of mountain ranges. The slow but constant release of geothermal energy helps maintain Earth's overall energy balance and contributes to the planet's ability to support liquid water and life. Underground water systems play crucial roles in transporting nutrients and minerals that support surface ecosystems. As groundwater flows through different rock formations, It dissolves essential elements like nitrogen, phosphorus, calcium, and magnesium. When this mineral-rich water reaches the surface through springs or river-based flow, it provides nutrients that support plant growth and ecosystem productivity. Many of the world's most fertile agricultural regions depend on nutrients transported by underground water systems. The interaction between underground and surface water creates wetland ecosystems that serve as crucial habitat for countless species and play important roles in regional climate regulation. Wetlands fed by groundwater discharge help moderate local temperatures through evaporational cooling and provide moisture that influences local precipitation patterns. These groundwater-dependent ecosystems often serve as refuges during droughts and support biodiversity in ways that depend entirely on the underground water systems that feed them. Underground biological activity influences surface ecosystems through complex chemical cycles that operate largely out of sight. Deep-dwelling microorganisms process sulfur, nitrogen, iron, and other elements in ways that affect the chemistry of groundwater and surface water. These underground biological processes can influence soil chemistry, plant nutrition, and water quality in surface ecosystems, creating connections between deep earth biology and surface life that scientists are only beginning to understand. The underground world also serves as a vast reservoir for many of the elements essential to life. Phosphorus, a crucial nutrient for all living things, is stored primarily in underground rock formations and made available to surface ecosystems through weathering and groundwater transport. Similarly, many trace elements essential for plant and animal health are stored underground and delivered to surface ecosystems through geological and hydrological processes. Climate change is revealing new aspects of the relationship between underground and surface systems. As global temperatures rise, the thermal balance between underground and surface environments is shifting in ways that affect both groundwater systems and surface climate patterns. Changes in precipitation patterns alter groundwater recharge rates, potentially affecting the underground water supplies that many ecosystems depend on during dry periods. The melting of permafrost in Arctic regions is exposing underground carbon stores that have been frozen for thousands of years. As this underground organic matter thaws and decomposes, it releases carbon dioxide and methane into the atmosphere, creating a feedback loop that accelerates climate change. This process demonstrates how changes in surface climate can trigger responses from underground systems that amplify the original changes. Underground heat storage and transport systems are being increasingly recognized as important factors in regional climate patterns. Large underground water systems can transport heat across great distances, creating climate effects far from where the heat was originally absorbed. Urban heat islands are partly caused by changes in underground thermal properties, when natural soil and rock are replaced by concrete and asphalt that have different thermal characteristics. The role of underground systems in supporting surface life extends beyond nutrient and water transport to include more subtle but equally important functions. Underground storage of organic matter helps regulate the timing of nutrient release to surface ecosystems. During growing seasons, increased biological activity in soil and shallow underground zones releases stored nutrients. During dormant seasons, nutrients are stored underground, preventing them from being lost through surface runoff. Underground biological communities also contribute to surface ecosystem health through their role in processing pollutants and contaminants. Deep-dwelling microorganisms can break down toxic compounds that filter down from surface activities, helping to protect groundwater quality and prevent contamination from reaching surface water bodies. This underground bioremediation capacity represents a crucial but often overlooked ecosystem service. The relationship between underground and surface systems becomes particularly apparent during extreme weather events. During hurricanes and intense storms, underground water systems can either absorb excess precipitation, reducing flood damage, or contribute to flooding if underground storage capacity is already exceeded. Understanding these underground contributions to flood and drought cycles is becoming increasingly important for predicting and managing extreme weather impacts. Underground systems also influence atmospheric composition through processes that operate on very long timescales. The weathering of underground rock formations consumes atmospheric carbon dioxide, slowly removing it from the atmosphere and storing it in underground carbonate minerals. This geological carbon sequestration process operates over millions of years, but plays a crucial role in Earth's long-term climate stability. The discovery of extensive underground ecosystems has revealed that the underground world supports far more biological activity than previously recognized. This hidden biomass represents a significant component of Earth's total living systems and plays important roles in global element cycles. Underground biological activity processes carbon, nitrogen, sulfur, and other elements in ways that affect global geochemical cycles and influence surface environmental conditions. Research into underground contributions to global cycles is revealing connections between deep Earth processes and surface environmental conditions that were previously unknown. Changes in underground water chemistry can affect ocean chemistry when groundwater discharges into coastal areas. Underground biological activity can influence atmospheric composition through the production of gases that eventually reach the surface. These discoveries are expanding our understanding of how Earth's systems are interconnected across the boundary between surface and subsurface environments. The underground world's role in supporting life extends to providing stability and resilience for surface ecosystems. Underground water storage helps ecosystems survive droughts that would otherwise eliminate surface water sources. Underground nutrient storage provides reserves that can sustain plant growth during periods when surface nutrient inputs are limited. Underground habitat provides refuge for many species during harsh surface conditions. As we continue to study the connections between underground and surface systems, we are discovering that the hidden world beneath our feet is far more active and important than we ever realized. The underground realm operates as Earth's life support system, regulating climate, cycling essential elements, storing and transporting water, and supporting biological activity that extends far beyond what we can see on the surface. Understanding these underground contributions to Earth's systems is becoming increasingly important as we face environmental challenges like climate change, water scarcity, and ecosystem degradation. The solutions to many of these challenges may depend partly on better understanding and management of underground systems that operate largely out of sight, but profoundly influence the surface world we depend on. The hidden world beneath our feet reminds us that Earth's environmental systems are far more complex and interconnected than surface observations alone might suggest. The ground beneath us is not simply a platform for surface life, but an active participant in the grand cycles that make our planet habitable and sustain the incredible diversity of life we see around us. The hidden world beneath is also a world of imagination. Throughout human history, the mysterious realm beneath our feet has captured the imagination of every culture on Earth, inspiring stories, myths, and beliefs that reveal as much about human nature as they do about our relationship with the underground world. These cultural perspectives remind us that the hidden depths below have always been more than just geological formations or scientific phenomena. They have been landscapes of the human soul, mirrors reflecting our deepest fears, hopes, and understanding of existence itself. Long before science could explain what lay beneath the ground, human beings created rich mythologies to understand the hidden world below their feet. These stories were not mere fantasies, but attempts to make sense of mysterious phenomena that surrounded our ancestors daily. The ground shook with earthquakes that seemed to come from some great power stirring in the depths. Springs bubbled up from unknown sources, providing life-giving water that seemed to emerge from the very heart of the earth. Caves opened like mouths into darkness so complete that they seemed to lead to other worlds entirely. In ancient Mesopotamia, one of humanity's earliest civilizations, the underworld was conceived as a vast realm beneath the surface world, ruled by powerful deities who controlled the fate of the dead and influenced the lives of the living. The Epic of Gilgamesh, one of the world's oldest surviving stories, describes a journey into this underground realm in search of immortality. The hero's descent into the depths represents humanity's eternal quest to understand what lies beyond the boundaries of the familiar world. The ancient Greeks developed perhaps the most detailed and influential mythology of the underworld in Western culture. Their vision of Hades was not simply a place of punishment, but a complex realm with its own geography, rivers, and regions. The river Styx flowed through the darkness, separating the world of the living from the realm of the dead. Elysian fields provided a paradise for heroes, while Tartarus served as a prison for those who had offended the gods. This underground world was as real and detailed in Greek imagination as any place on Earth's surface. Greek mythology also gave us the story of Persephone, whose annual journey between the surface world and the underworld explained the changing of the seasons. When Persephone descended to the underground realm, the earth above mourned her absence and winter came to the land. When she returned to the surface, life bloomed again in celebration of her presence. This myth represents one of humanity's earliest attempts to understand the connection between underground forces and surface phenomena. The Romans inherited much of Greek mythology, but added their own perspectives on the underground world. Roman engineering achievements, including extensive underground aqueduct systems and underground burial chambers called catacombs, reflected a more practical relationship with the subterranean realm. Yet they too maintained rich mythological traditions about underground spaces, often associating them with prophecy, hidden knowledge, and connection to divine powers. Norse mythology presents a different vision of the underground world, one that emphasizes its connection to the great world tree, Yggdrasil. In this cosmology, multiple realms exist beneath the surface, connected by the tree's roots, and inhabited by various beings including dwarfs, who were master craftsmen living in underground halls and caves. The Norse underworld was not primarily a place of the dead, but a vital part of an interconnected cosmic system where different types of beings played important roles in maintaining the balance of existence. Hindu cosmology describes multiple levels of reality existing beneath the surface world, each with its own characteristics and inhabitants. These underground realms are not simply places of punishment or reward, but integral parts of a complex universe where different forms of consciousness exist at different levels. The underground worlds in Hindu mythology are often described as more beautiful and advanced than the surface world, suggesting a view of the depths as places of wisdom and spiritual development rather than darkness and fear. Buddhist traditions also include extensive descriptions of underground realms, often focusing on their role in spiritual development and the journey toward enlightenment. Underground spaces in Buddhist thought are frequently associated with meditation, retreat from the surface world's distractions, and the deep inner work necessary for spiritual growth. The cave where the Buddha achieved enlightenment has inspired countless stories of underground spaces as places of profound spiritual transformation. Native American traditions across North and South America include rich mythologies about underground worlds that often emphasize their connection to the origins of life and the source of spiritual power. Many creation stories describe the first people emerging from underground realms into the surface world. These emergence myths often portray the underground as a place of preparation and growth, where beings develop the qualities necessary for life in the upper world. The Hopi people of the American Southwest maintain detailed oral traditions about multiple underground worlds that humanity has inhabited throughout its history. According to these traditions, people have emerged from previous underground worlds when conditions on the surface became uninhabitable, suggesting a cyclical relationship between surface and underground existence that spans vast periods of time. Aboriginal Australian cultures include Dreamtime stories that describe the underground realm as a place where ancestral spirits continue to exist and influence the surface world. The underground is seen as a repository of ancient wisdom and spiritual power that can be accessed through ceremony, meditation, and proper relationship with the land. These traditions emphasize the ongoing connection between surface and underground worlds rather than viewing them as separate realms. Celtic mythology is rich with stories of underground realms that exist parallel to the surface world, often accessible through special entrances like caves, wells, or ancient burial mounds. These underground worlds are typically described as places of magic and wonder, inhabited by fairy folk and other supernatural beings. The Celtic otherworld is not a distant heaven or hell, but an alternate reality that exists alongside and sometimes intersects with ordinary surface existence. African mythological traditions include numerous stories about underground worlds that serve various functions in explaining natural phenomena and human experience. Some traditions describe underground realms as the homes of ancestors who continue to influence the lives of their descendants. Others portray underground spaces as sources of wisdom, healing power, or spiritual transformation that can be accessed by those with proper knowledge and preparation. Asian cultures have developed sophisticated mythologies about underground worlds that often emphasize their role as sources of wisdom and spiritual power. Chinese mythology includes stories of underground kingdoms populated by dragons and other powerful beings who control water, weather, and fertility. Japanese traditions describe underground realms inhabited by spirits and supernatural beings who influence human affairs and natural phenomena. The influence of underground mythology extends far beyond ancient cultures into modern literature, art, and popular culture. Dante's Divine Comedy presents one of the most detailed and influential literary descriptions of an underground realm, complete with multiple levels, complex geography, and profound spiritual significance. Dante's Hell is not simply a place of punishment, but a carefully structured representation of human moral and spiritual development. Jules Verne's Journey to the Center of the Earth popularized scientific speculation about underground worlds and inspired generations of writers and explorers to imagine what might exist in the depths below. This novel reflects the 19th century fascination with scientific exploration, while maintaining the sense of wonder and mystery that has always surrounded the underground realm. Modern fantasy and science fiction continue to draw inspiration from ancient underground mythologies, while incorporating contemporary scientific understanding. Stories of underground civilizations, hidden kingdoms beneath the earth, and journeys into mysterious depths remain popular themes that resonate with fundamental human fascinations about what lies beneath the familiar surface world. The psychological significance of underground mythology reveals deep aspects of human consciousness and imagination. Underground realms often represent the unconscious mind, the hidden aspects of personality, or the mysterious forces that influence human behavior from below the level of conscious awareness. The descent into underground worlds frequently symbolizes psychological or spiritual journeys into the depths of human experience. Archaeological discoveries have revealed that many ancient cultures created actual underground spaces that reflected their mythological beliefs about the subterranean realm. Underground temples, burial chambers, and ceremonial caves demonstrate that the mythological underground was not just an abstract concept, but influenced real architectural and cultural practices. These underground constructions often incorporated sophisticated engineering and artistic elements that rival any surface achievements. The continuing appeal of underground mythology in contemporary culture suggests that these ancient themes still resonate with modern human experience. Movies, books, games, and other forms of entertainment regularly feature underground worlds that echo ancient mythological themes while incorporating modern concerns and technologies. The underground realm continues to serve as a metaphor for the unknown, the mysterious, and the transformative aspects of human experience. Environmental and ecological perspectives on underground mythology reveal how these stories often encoded practical knowledge about underground water sources, cave systems, and geological phenomena. Many mythological descriptions of underground realms include details that correspond to actual underground features, suggesting that ancient mythologies preserved important practical knowledge about the subterranean world within their narrative frameworks. The relationship between underground mythology and actual underground exploration demonstrates how cultural beliefs have influenced scientific and practical investigations of the subterranean realm. Many early explorers and scientists were motivated partly by mythological curiosity about what might exist in underground spaces, and their discoveries often both confirmed and challenged traditional mythological understanding. Contemporary spiritual and religious movements continue to find inspiration in underground symbolism and mythology. Meditation practices that emphasize descent into inner depths, retreat practices that utilize actual underground spaces, and spiritual traditions that honor the earth and its hidden dimensions all reflect ongoing connections between underground mythology and lived spiritual experience. The study of underground mythology also reveals how different cultures have understood the relationship between life and death, known and unknown, visible and invisible. Underground realms often serve as bridges between these paired concepts, places where normal rules don't apply and transformation becomes possible. These mythological functions help explain why underground symbolism remains powerful and relevant even in scientific and technological societies. As we reflect on the rich cultural and mythological traditions surrounding the underground world, we recognize that the hidden realm beneath our feet has always been more than just a physical space. It has been a canvas for human imagination, a repository for our deepest questions about existence, and a source of stories that help us understand our place in the larger cosmos. The underground world of mythology reminds us that beneath the scientific facts and geological processes lies a realm that speaks to something fundamental in human nature, our eternal curiosity about what lies beyond the boundaries of the known and familiar. As our journey through the hidden world beneath our feet draws to a close, we find ourselves standing once again on familiar ground, yet everything has changed. The solid earth beneath us is no longer simply dirt and rock, but a gateway to wonders that rival anything in the most distant galaxies. We have traveled through layers of stone and time, discovered life thriving in eternal darkness, and witnessed forces that shape our planet from the inside out. The ground on which you rest as you listen to these words is the thin ceiling of a universe as vast and mysterious as the cosmos above. Beneath your feet, ancient waters flow through channels carved by millions of years of patient erosion. Microorganisms older than human civilization continue their slow dance of survival in conditions that would seem alien to any surface dweller. Vast chambers carved from solid rock stretch into darkness, harboring ecosystems that operate by rules entirely different from those governing the familiar world above. We have learned that the underground realm is not a static, lifeless foundation, but a dynamic, living system that breathes with our planet's pulse. The carbon stored in deep rocks helps regulate our climate across geological ages. Underground water systems transport nutrients and energy across continents, sustaining surface life in ways we are only beginning to understand. The heat flowing from Earth's core drives the forces that built the mountains and carved the valleys of our surface world. In the deepest mines and bore holes, humans have pushed the boundaries of exploration, reaching depths that would have seemed impossible to earlier generations. Yet these achievements, impressive as they are, represent only the smallest scratches on the surface of Earth's interior realm. We have penetrated less than 1% of the distance to our planet's center, leaving vast volumes of underground space still unexplored and unknown. The creatures we have encountered in this hidden world remind us that life is far more adaptable and persistent than we ever imagined. In chambers where no sunlight has ever penetrated, where temperatures would boil surface water, where pressures would crush any surface structure, life not only survives, but thrives. These underground ecosystems show us that our planet supports forms of existence so exotic, they challenge our basic understanding of what life can become. The stories and myths that humans have created about the underground world reveal something profound about our relationship with the unknown. Across cultures and throughout history, the realm beneath our feet has served as a landscape of imagination, a place where we project our deepest fears and highest hopes. These stories remind us that the underground world is not just a scientific phenomenon, but a space that speaks to something fundamental in human nature. The technologies we have developed to explore and understand the underground realm continue to push the boundaries of human capability. From the sophisticated instruments that map Earth's interior using earthquake waves to the robots that explore underwater caves, our tools for investigating the hidden world grow more advanced with each passing year. Yet every new discovery seems to reveal that the underground realm is even more complex and mysterious than we previously imagined. As we contemplate the vast scope of what we have learned about the world beneath our feet, we are struck by how much remains unknown. The deep biosphere may contain more living organisms than exist on Earth's entire surface, yet we have studied only a tiny fraction of these underground communities. Vast underground water systems transport chemical and biological materials across continents, yet we understand only the basic outlines of these hidden circulation patterns. The underground world challenges us to expand our perspective on what constitutes our planet's living systems. We have long thought of Earth's biosphere as primarily a surface phenomenon, a thin skin of life existing at the boundary between rock and atmosphere. Now we know that this biosphere extends deep into the Earth, creating three-dimensional ecosystems that span from the deepest ocean trenches to miles below the continents. The hidden world beneath our feet also offers hope for understanding life beyond our planet. If organisms can thrive in the extreme conditions found deep within Earth, They suggest possibilities for life in the subsurface environments of Mars, Europa, Enceladus, and other worlds in our solar system. The underground biosphere provides a template for how life might persist in harsh planetary environments where surface conditions seem uninhabitable. The relationship between surface and underground systems reminds us that our planet operates as an integrated whole, where processes spanning from the core to the atmosphere work together to create the conditions that support life. The underground realm is not separate from the surface world we know, but an integral part of the same dynamic system that makes Earth unique among the planets we have studied. As we face environmental challenges like climate change, water scarcity, and ecosystem degradation, understanding the underground world becomes increasingly important. The solutions to many of these challenges may depend partly on better understanding and management of underground systems that operate largely out of sight but profoundly influence surface conditions. The underground world holds resources, processes, and capabilities that may be essential for maintaining the planet's habitability. The exploration of the underground realm also offers practical benefits that extend far beyond scientific curiosity. Underground spaces provide opportunities for energy storage, waste disposal, and protection from surface environmental hazards. Underground water systems offer resources for agriculture and urban development. Underground biological processes offer potential applications in biotechnology, environmental cleanup, and industrial production. Yet perhaps the greatest gift of our journey into the hidden world beneath our feet is the sense of wonder and humility it inspires. In an age when satellite imagery can map Earth's surface in extraordinary detail, when we have sent spacecraft to the edge of the solar system and observed galaxies billions of light years away, the underground realm remains largely unknown. It reminds us that genuine frontiers for exploration and discovery still exist, that our own planet still holds mysteries as profound as any we might find in the depths of space. The underground world teaches us patience, showing us processes that unfold over time, scales that dwarf human experience. The bacteria living miles below the surface may be thousands of years old, individual organisms whose lifespans bridge the gap between biological and geological time. The underground rivers flow at rates measured in feet per year rather than miles per hour. The caves are carved by processes so gradual that millions of human generations could pass before significant changes become apparent. This deep time perspective, offered by the underground world, provides a valuable counterbalance to the rapid pace of modern surface life. It reminds us that some of the most important and fundamental processes on our planet operate on timescales that require patience and long-term thinking to understand. The underground realm offers lessons in persistence, resilience, and the power of gradual change that may be essential for addressing the long-term challenges facing our surface world. As you settle into rest tonight, imagine the incredible world that exists just beneath where you lie. Feel the weight of the earth supporting you, but know that this support comes not from dead rock, but from a living, breathing, dynamic system that connects you to forces and processes spanning the entire planet. The ground beneath you is alive with movement, growth, and change that continues regardless of whether the surface world sleeps or wakes. Let your mind sink slowly downward through the layers we have explored together, past the soil where roots reach toward hidden water, past the caves where strange creatures navigate by senses we can barely imagine, past the underground rivers that have flowed in darkness for millions of years, down into the deep where life persists in forms so exotic they seem to belong to another world entirely. Rest, knowing that you are supported not just by solid ground, but by a realm of wonders that extends far beyond what any human has ever directly experienced. The hidden world beneath your feet is as vast and mysterious as the cosmos above your head, filled with discoveries waiting to be made and stories waiting to be told. The underground world reminds us that no matter how much we learn about our planet, there will always be deeper mysteries to explore, new frontiers to investigate, and unexpected discoveries to make. Beneath our feet lies a world as alien as any distant planet, yet as close as the ground on which we rest. It is a world that humbles us, reminding us that even the familiar earth beneath our feet holds secrets vast enough to inspire wonder for generations to come. Beneath the ground we walk, a secret realm stretches far beyond what we can see, dark, quiet, and mysterious. It is a world of ancient rocks, hidden waters, and life that thrives in eternal night. It waits patiently in the darkness, ready to reveal its secrets to those curious enough to look deeper, brave enough to explore further, and wise enough to listen to the stories whispered by stones that have waited millions of years to tell their tales.